So today we will begin discussing two-dimensional finite element analysis. Since we are looking at a week-long break due to mid-semesters, so what I would do in today's class is to make you think in terms of transitioning from 1D to 2D. What exactly is two-dimensional analysis? And whatever logic I give will apply to three-dimensional analysis also. What is two-dimensional analysis? How do I go from 1D to 2D? What are the new things that come? Let us try to get that perspective first clear before we get into the details of exactly doing a two-dimensional finite element development. So my focus will be in today's class to primarily get across to you what are the challenges in going from 1D and 2D. 1D we have now thoroughly understood. So I am assuming that you are now well versed with one-dimensional FEM. So let's see how this goes. So I take a concrete example to illustrate what is in 2D. Okay. So look at a very familiar problem. Most of you must be familiar with this. This picture is showing a pair of gear teeth in mesh. So we want to find out, say, the stresses. You may want to find out if there is any excessive stress buildup, eventually leading to failure. You may also want to ask the question, would there be excessive amount of noise generated in this gearbox? So like that we want to analyze this in the computer now. In the olden days, the design used to be based on certain handbook formulae, okay, and rules of thumb, some design charts and so on and so forth. Say using all those, you have made a preliminary design. Now you are trying to analyze it to see how good is your design. If you look at it, a gear tooth has a gear pair has a set of gear teeth, maybe involute, cycloid or whatever. It has certain face width, height or depth of gears, and a pair of gear teeth will come into mesh and go out of mesh. So this is no longer, really speaking, a time independent problem as we have been discussing so far. So if you want to make a complete analysis of this system, you have to bring in time. Okay, we note that first. Okay, let me say that time is incorporated. Then what else? So now if you look at this, this seems to me like unlike all the examples I have taken earlier, which is one-dimensional means only the domain was 0 to L, one line. Now this seems to be actually a three-dimensional domain. So it appears to me that perhaps I should do a three-dimensional analysis. If you look at it in that sense, every problem in the real world is a three-dimensional problem. Most of the times, the domain expands into x, y and z directions considerably. So you may be tempted to think that every problem in the real world is a three-dimensional problem. And I should be discussing only three-dimensional finite element analysis, nothing else. But if you start looking at every problem as a three-dimensional problem, then even when you did courses on solid mechanics, fluid mechanics or electromagnetics, the governing differential equations would have been partial differential equations in 2 or 3 dimensions, and then you would have asked for solutions for those. Since you have already done a course on partial differential equations, probably you would know that it is much harder problem to solve than ODEs. So we try to simplify wherever possible. What is the meaning of this simplification? So the question is posed not in terms of the geometry of the system, but in terms of how the field variable, let it be displacement, strain, stress, etc., or temperature, fluid flow velocities, whatever, electromagnetic fluxes, the field variable, how it varies along the 3 coordinate directions. That's the fundamental question you should ask. Then you can ask the question along any 1 or 2 directions if possible. Can I make reasonable assumptions about the way in which the field variable changes? For example, if along the thickness of this gear, okay, that is along the axial direction, if everything is same, okay, strains, stresses, deformations are going to be same, then I can say that I don't have to worry about modeling the z direction. I will focus only on the variation in the r and theta plane. Okay. So that is a question that we have to ask first whenever you look at a problem. What is the field variable? How is it varying along the 3 coordinate directions? Is there a scope for me to make an intelligent, informed guess about the variation of the field variable in at least one direction? Like here I have said, if it is likely to be a constant, which that is the case, and I can actually remove the z direction altogether. I don't model thickness at all. Whatever I model in one plane, I will assume it will apply to any other plane along the thickness of the gear teeth. So, on the left side I have shown a finite element mesh which has only 2-dimensional elements. These elements, when I say 2 dimensions, it is not that they don't have thickness. It is implying that along the thickness direction, the field variable is varying in a known manner, which you can assume, and therefore it is out of finite element computation. Okay, that is the understanding of 1D or 2D or 3D. When I talked about 1D, of course, because you have been already taught all those subjects, we didn't get into the discussion on how it became 1D. For example, when I talked about the axial deformation of a rod or of even a beam, for the rod, our assumption was that we did a thought experiment. We assumed that this rod is made up of millions of longitudinal fibers, and when I apply a load or pull, all of these fibers move together. So, if this was a cross section here, after deformation it would have moved here, the entire cross section remains the same, it just parallelly moves like this. So, therefore, I knocked out the entire cross section. I need to know only along the length how the deformation is changing, because the cross section is fixed for me. Immediately, the moment I know that this point has moved from here to there, I know that the entire cross section would have moved. That's a reasonable assumption I felt, I made it. That is how 2 dimensions were knocked off along y and along z. Only along x remained. Here I am saying that along r and theta plane, I can't make any reasonable assumption. I don't know how it would vary. But whatever is there in this plane seems to be okay along the thickness. So, therefore, I am knocking off thickness. I will consider only this plane for finite element modeling. And whatever results I find for deflection, strain, stresses or fluid velocities or whatever it is, I assume that it is applicable across the entire thickness. Okay. So, keep that perspective in mind. Of course, in this particular problem, it is further possible to look at this and say that there is an inherent geometry symmetry. All we are having is, if there are 20, 40, 60 teeth, it is just one tooth that is repeated so many times around the circumference. So, is it possible that the response, deformations, strains and stresses would also vary around the circumference in a similar manner? Because what is happening is that one pair of tooth gets into contact and gets out of contact, then next pair like this, and after one round the same tooth comes back in contact, and then next round, next tooth, and so on and so forth. So it is the same thing that is getting repeated again and again. So if I were to consider focus on one gear pair, okay, or maybe if not one, okay, because of the contact ratio issues, etc. So maybe you can take a 2 or 3 gear teeth as one unit. If you are able to analyze that, then would everything else be similar? Is the natural question that comes to your mind. That is also possible. So that we would call as what is known as cyclic symmetry. It is cyclically repeating itself. Okay. So it is possible to do that type of analysis also. So even within 2D, I am not taking theta 0 to 360, but I am taking only a segment which contains a representative number of gear teeth in mesh, and then everywhere else I assume that it will be similar. So this is how you can simplify the model, and within whatever is the zone that you have taken for analysis, you can do H refinement, P refinement, whatever you want to get the best results possible within the computational resources available to you. That is the approach we will take. So you could do a very coarse mesh if you want to just try it out and see that whether you are getting some reasonable results, and are they matching with your handbook design formulae that you have used, or you could do a very fine mesh. But the domain is simplified based on all the considerations that I have just now mentioned. So when you are doing your course projects, you can do this type of thinking to your problem at hand. Don't have to blindly use the software 3-dimensional elements for every problem whatever you are solving. You can analyze, and sometimes even for validation purposes you may want to simplify the problem to see how the results are, how are they varying. Supposing I am making the gear tooth stubbier or bigger, longer, how are the results varying? Is that making sense to you, your understanding of the problem as an engineer? So can I rely on the finite element results that I am getting, or is it simply something that I have put in and something that is coming out of the software? Okay. So then you may not want to do a very detailed refined mesh with a large number of elements, but you may want to do with a coarser mesh, but try out various parameters and see if the change in the results is on expected lines. Then you get more confidence on your finite element model of the domain, boundary conditions, loading, material properties, all these things. Once you are confident, then you go ahead with full-fledged finite element analysis with refined mesh. So when you are doing your course projects, when you make your presentations, we expect that you show such awareness of the fundamental principles of engineering analysis. So as I mentioned just now, so the crucial question to ask is not just about how the domain of the problem is, but about the variation of the field variable along the 3 coordinate directions, and of course with respect to time. Okay. Can you ignore variation with respect to time? Can we say that it has reached steady state? Can we say that it would repeat periodically with respect to time? Okay. Like this kind of questions you can ask for yourself and then try to simplify the analysis problem. Now I will mention with some examples in structural mechanics, say, how a problem becomes a 2-dimensional problem. So I will take 3 specific cases which are listed in this slide: plane stress, plane strain, and axisymmetric. What do we mean by these things, and how does a 3-dimensional problem become 2-dimensional because of this type of a feature? So the first one is plane stress. The classic example that you can think of is a thin disc like this. Okay. It is like there is no ceiling fan in this room. Otherwise, you can think of the ceiling fan disc and the blades. Okay. So that system is rotating. It is actually very thin. It is rotating in its own plane. Self weight is negligible, say. So the loading is in its own plane due to the rotation, mr omega squared kind of forces. As it rotates, the loading is in its own plane. So I would assume that the stresses also will be restricted to this plane. Whatever is the stress, normal direction would be 0, because the normal direction stress at the top is 0. It is a free surface. At the bottom it is 0, and it is very thin. So even if it existed, it varies from 0 at the top to 0 to the bottom, and in between whatever little variation it has only this much thickness to undergo that variation. So I would tend to make an assumption that perhaps the normal stress is 0 throughout. You understand my point? So if I am considering only in-plane forces of a thin disk, then I could come up with such assumptions. Then I can ignore what happens in thickness. Of course, there will be minor variations, like, I mean, you can think of a grinding wheel, for example. Grinding wheel is stubby, it has abrasive material here, and it does grinding only in this direction, tangential direction. When it acts on the surface, forces are there. So given that, you can consider that the thickness direction, the stresses are 0, and so I can analyze only this plane. The wheel of an automobile rotating in its own plane. So you can think in terms of such examples of very thin structures which are subjected to forces only in its own plane, not out of plane, and therefore out of plane stresses are 0 throughout the entire volume of the material. It's an assumption that I am making. May be true or may not be true, will only be validated by experiment. There is no other way to validate something like this, because once I assume this, all my analysis, even if you do finite element analysis, the results will be consistent only with that assumption. So I can't, unless I do a 3D analysis, then I can compare with this. So if that is the case, sigma z is 0, then there are 3 components of stress: sigma x, sigma y, and the shear stress in this plane. I am assuming that most of you are familiar with this. If you are not, please feel free to ask me at this point. And we generalize the Hooke's law to find the stress-strain relation between these quantities. So how you get it is epsilon x. When you studied Hooke's law, epsilon x is sigma x upon E, if it is one dimension, minus, what did I use? Nu pi. But this is not 0, it is not there. Right now it is 0. So this is what we have. Similarly, epsilon y, by virtue of Hooke's law, is sigma y upon E minus Poisson's ratio times sigma x upon E. The shear strain is shear stress by modulus of rigidity. Of course, this you would have related, modulus of rigidity you would have related to the Young's modulus. I have put it in matrix form as a relation between stresses and strains. Okay. The strains are related to the displacements. Okay. So that's how I would use this relation later on when I formulate the 2-dimensional elements. Stress is related to strain is related to displacement at a point, and derivatives, rate of change of displacement at a point. So the displacement at a point are interpolated from the nodal values of displacement. That's how the chain of calculations will go. Okay. So we will come to that a little later. Plane strain is exactly the opposite case, where rather than a thin structure, I am looking at a structure which is very long, then I would tend to think that epsilon z, change in length by original length, is 0. But sigma z is not 0. Epsilon z, strain, longitudinal strain is 0. So sometimes we make this assumption that plane strain conditions. Again, the analysis will be two-dimensional. When I say that sigma z is not 0, then why am I saying it is still a two-dimensional problem? Because sigma z not being 0, it is still can be computed from epsilon x and epsilon y and epsilon z being 0. That is the point. So it is a known thing. It is not something unknown variation of the strain or stress or deformation that you need to calculate using finite element analysis. So therefore, it is still a two-dimensional problem. Or another interesting case we come across many a time is that of an axisymmetric problem. Axisymmetric problem would mean like the geometry is symmetric right here. So the geometry is symmetric about the longitudinal axis, right? So if I were to take any section, I can just think of the entire geometry being made up of by rotating this about the axis. So that is why it is called an axisymmetric geometry, like cylinders with conical shapes and caps. Okay, those are typical pressure vessel structures. Okay. Now that is not enough. If this fellow I take and I hold it here and subject it to a force like this, then the resulting stresses will not be axisymmetric. Or this is a pressure vessel or a tall tower that you have built and it is subjected to an earthquake. Then again, the resulting stresses will not be symmetric. So it has to be symmetric geometry, symmetric loading, as it would happen in the case of, say, a pressure vessel. The internal pressure or external pressure, of course, if it is symmetric all around 360 degrees, then I would tend to think geometry is symmetric, loading be symmetric hai, so maybe response stresses will be also symmetric about this axis. So I don't need to consider theta from 0 to 360 degrees. If I consider any one section, that's good enough. Everywhere else it will be the same thing. Okay. So therefore, again from three-dimensional problem, I can bring it down to two dimensions. The two dimensions here will be the radial plane and the axial plane. Theta has been knocked out. So my finite element domain to be modeled will only be this piece, which is in the r and z coordinates. Is that making sense? But then you may ask the question, and since I am asking this question, you didn't ask, even though I put it into your mouth, you will have to tell me the answer. Is it enough if geometry is symmetric and loading is symmetric? Pardon? Boundary conditions have to be symmetric. Why do you say boundary conditions have to be symmetric? If I have this cylindrical geometry, I have subjected it to a load which is like internal pressure, which is symmetric, but I have not held it at one end or whatever boundary condition I am doing, all around, but at some selected point, okay, then that fellow is not axisymmetric. It will not permit axisymmetric variation of displacement, strain and stress. Okay. Is it enough if boundary condition is axisymmetric? Pardon? Material properties. This is an interesting point because we generally assume a material to be linear, elastic, homogeneous, isotropic, etc. So therefore, we sometimes fall into the trap of forgetting it and just assume that it is something that satisfies Hooke's law, so ho gaya kaam. But that is not really the case. Now we are talking in terms of very complex materials. Okay, composite materials, for example, are now everywhere used, in all structures. So, if this pressure vessel is made up of such composite materials, or it has been designed in such a way that the material you have does not have properties same all around the circumference, 0 to 360 degrees. Then for the same geometry, for the same force which is symmetric about this axis, boundary conditions are symmetric, but material will not deform symmetrically. So, you would be able to make these kind of assumptions only when all these factors are cooperating with you. That is boundary conditions, material properties, loads, geometry, tick, 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 then okay, I can make a reasonable assumption that this is a axisymmetric problem. Okay. But if it is, say, subjected to, okay, material is axisymmetric, boundary conditions are axisymmetric, geometry is axisymmetric, but say it is not subjected to internal pressure only, it is subjected to some force like this. Okay. Can I still make some assumptions about how the response will be and do a two-dimensional analysis, or no, I have to do a complete three-dimensional analysis only? Only loading is not obliging you. It is not symmetric. So, if I am applying a force here, I am not applying all around the circumference. What can you do in such a case? Can we think in some way cleverly to come up with a model? Cross-sectional plane meaning like this. Okay, cross-sectional plane like this. And then the section you consider may not actually include the loading point. Parallel to the force, you will cut it. But that force is not all around, right? So, what assumption can I make about the expected response? What do you see about this problem? What strikes you when you look at something like this? I am emphasizing these aspects of modeling because you guys are going to do course project now. You are warmed up. Today is the date for submitting your course projects, first stage, whatever preliminary work you are doing. So, you are all warmed up, okay, or in the context of the example we are thinking of, you are all geared up. So, you should think in terms of modeling a physical problem into mathematical problem and correspondingly computational model for finite element. So, there is a physical problem which to be converted to mathematical model, which is to be converted into a computational model. Okay. Then the fourth and final one is of course an experimental model. So, I am trying to make you think, what do you think of, say, temperatures or deformations or whatever it is whenever you look at something like this? I start from here, ting, 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 I go around and then I come back here. What does it trigger in your mind? It will be constant. Okay. What else can we think of? Similar to gear problem means what? So, I am visually giving you the clue. So, I am going around starting from some point, theta is equal to say 10 degrees, go around, down, come back. When I have completed 360 degrees of rotation, I come back to the same point. Then I can go around like this, I will come back again to the same point, again to the same point. Anything else you can think of? What is the expected behavior of f of x that we are trying to determine? Temperature, wave, displacement ho, temperature ho, whatever. F of theta. let's say, instead of saying f of x, f of theta. It would be a function of theta, I agree, but what type of a function of theta? 0 से शुरू किया, 2 pi periodic. इतना देर लगा to get you out of you fellows. You expect the solution has to be periodic, right? With periodicity 2 pi. So now come back to the question with which I started. Everything is boundaries, conditions are there, material is there, geometry is there, but load alone or any one of them, I am just trying to get you to think. Any one of them, like say the force, is not same around the circumference. So you are not able to do axisymmetry. But is there something else that you have done in maths that you could use? Once you have agreed that these are periodic functions and still get away with a two-dimensional analysis. So think it over. Okay. I want you to start thinking like this when you are looking at a practical problem. Course project mein liya hai. So if you want to do finite element analysis of that, don't immediately jump into the computer, sitting in front of it, do some modeling. Don't do such things. I see a large number of students all the time sitting in front of the computer. Take some time to go for a walk in your hostel or park or whatever. Think about the problem, see how you can model it. What exactly is the problem? What are the questions you are trying to answer out of that? How you can model it? How do you think, without doing all this analysis, how do you think the solution would be like? Can you make some intelligent guesses about the solution? Okay. That is when you can really, say that you have gained some insights into the course. Okay. So think about that. Now coming back to this, if everything is cooperating with you and you are able to make an axisymmetric element, analysis kind of a assumption, then you would take only one plane like this, RZ plane, because around that theta 0 to 2 pi is all constant, so you don't have to worry about it. So again, it is a two-dimensional domain for finite element analysis. But interesting point you have to understand here is like earlier two-dimensional things, it has sigma r and sigma z. Okay, sigma r, sigma z, yes. But whenever radius changes, circumference will have to change. So there has to be sigma theta now. The radial stress has got to be accompanied with a circumferential stress. As radius r becomes r plus delta r, then circumference 2 pi r has become 2 pi r plus 2 pi delta r. So there is a circumferential strain. So there will be an additional stress component. So that is why your Hooke's laws would be a little different. There are 4 components of stresses and 4 components of strain. If you look at plane stress or plane strain, there were only 3 components of stress and strain. But when it comes to axisymmetric, because of this link between radial and circumferential direction, even though you have knocked out circumferential direction, that stress will be there, that strain will be there, and therefore it is a more complicated relation straight out of Hooke's law, nothing else. This is just a generalization of Hooke's law. Using Poisson's ratio, you will get this stress strain. But all these are actually part of your course if you did an ME601 or whatever, stress analysis course, solid mechanics, advanced solid mechanics and so on and so forth. Okay. We are only going to use these relations when I look at finite elements, two-dimensional finite elements for structural mechanics problem. Similar relations will be there for heat transfer or fluid flow or whatever. Now, let's think of, now we have understood so far how a problem can be modeled, first of all, as a 3D or 2D or even 1D. Without telling all these complications, I have introduced you to only directly one dimensional. But now that you have matured in the subject, I am asking you to think in terms of really whether a problem is 1D or 2D or 3D or even 4D, if time also has to be brought into picture. Now I will ask you to slowly think deeper as we want to transition from one dimension to two dimension. What are the additional challenges that come up? When it was one dimension, the geometry was just a line. Whether I took one element over the entire domain or two elements or 200 elements, 200,000 elements, all that I had to do was 0 to L, divide it into small number of elements pieces. Now think in terms of what happens if I go extend this to two dimensions. Okay. What I did here was to take the entire domain into bits and pieces, and over each piece element I have a linear variation of unknown variable or a quadratic variation or whatever, cubic variation if it was a beam element. So, modeling of the geometry, and over that geometry, which was just a single line, how is the field variable temperature, displacement, etc. varying? These are two aspects that we considered. The first aspect in one-dimensional analysis was a no-brainer. We really didn't even discuss it. It was not an important thing for us because it is just a line, you are cutting into pieces. But now what happens to this question when I go into two dimensions? So if you extend this logic, there is a two-dimensional domain, like for example this. Okay. So length is there, breadth is there, they are comparable in dimensions, thickness is small, so I have assumed that temperature or velocity or stress don't vary in the thickness. So I have reduced the problem to two dimension, but these two directions I cannot make any intelligent guess or assumption. So I need to find using FEM how the field variable is changing along x and along y. Fair enough. So I need to think of what is the surface which is f of x y now. All along it was f of x, now it has become f of x y, f being temperature or displacement or velocity or whatever. So f of x y needs to be modeled. So that is a simple extension of 1D to 2D. Instead of f of x, I have to model f of x y. So f of x, so it was only a curve. That curve over this domain 0 to L, I modeled it using straight line segments or linear or quadratic or cubic segments. But when it comes to here, over this domain, the temperature varies and it is a surface. That surface will be approximated using some shape or interpolation functions. That line could become a triangle or a quadrilateral plane. That quadratic curve that I took or a cubic curve I took could become a more complex shaped surface over that element. So I have to approximate this whole surface with bits and pieces of either planes or they themselves could be distorted surfaces. That is modeling the field variable. That is easy to imagine extending from one dimension to two dimension. But a new problem has come up for us, which you must notice now, is about modeling this two-dimensional geometry. Okay. I have to model this geometry means if it were like extending blindly from one dimension I took lot of straight lines, cut it into pieces. Now I will make it into lots of say rectangular or square elements. But life is not that simple. If you look at this simple mobile phone that I am holding in my hand, if I were to model its geometry accurately, then you have to see how the corners are curved. Okay. I need to model these corners being curved properly. Okay. Because often the solution depends on those corners, geometry features. Imagine an airplane whose wings do not have aerodynamic profile, right? So that aerodynamic profile is very crucial for the performance of the aeroplane wing. So when I am modeling an object in 2D or 3D now, I should model the geometry as accurately as possible. Because all of you know that the geometry would determine the solution now. The fluid flow and the turbulence that comes and the vortices that would come or not come, all this will depend upon how the geometry is. Whether there will be concentration of stresses leading to shoot up in the stress values and then ultimately failure there will depend upon how much fillet radius you have given. If two objects are joining, if you have welded them, how well you have given the fillet radius, chamfer. That will determine how much is the stress. Now I cannot simply ignore that. I have to model that geometric feature accurately. There may be some hole inside. So materially nahi hai, it's a hole. Now type of hole, so that hole could represent the windows in the fuselage of an aircraft. So the type of the window, whether it is elliptical, whether it is rectangular with corners, circular holes, will vary, will change the way in which the stresses will vary. So I have to model now, not simply as cutting it into pieces. A line element in 2 dimension you would think of as a triangle or a quadrilateral, correct? But that's not how simple life will be now. It is possible that the geometry actually has a circular hole. However much you may try, you may not get an exact circle in your computer model. That means what? You have either added more material or modeled less material, because you couldn't get exactly the same circular hole there. So this is a new error that has crept into your model, which was not a problem for one-dimensional model. When you go now to 2D and 3D models, if you were to do a thought experiment, this is what I am modeling. So I actually put it in a weighing scale and check the weight of this, and do the same thought experiment in the computer model and find its weight. These two may not match, because you have goofed in some of these geometric features. Material density you may give the same value, but these two may not match. So while modeling the geometry, you could potentially introduce a new error now. We would call this as discretization error. This discretization error did not exist in one-dimensional problems, because all I am doing is just 0 to L, I am cutting it into pieces. So one piece after another piece after another, that never occurred to us. But here now it is a real possibility. You might goof in modeling the geometry itself. So you have to introduce curvature into your elements. It is not sufficient if you have just straight edged elements. You have to bring in curved elements. Now, but how much curvature can you put in? Somebody may put an elliptical hole, somebody may put a circular hole, or somebody may put a corner like this. If you look at the way in which you just, after the class when you are going out, you look at the parking lot, there are a variety of vehicles parked in the parking lot, right? All of them has essentially 4 wheels and an engine and take you from place A to place B. right? That's all they will, functionally that is all they will do. Some may take you faster, some may take you more comfortably, etc., etc. But when you look at the car, you would like some car design, and some you may think that no, this doesn't look good. That would depend upon what? Car styling. If you look at now how it impacts the aerodynamic performance of the car, when you say now, when you are going at a high speed on a highway, how much is the drag? How you can reduce the fuel consumption? This depends upon that styling of the car, how you are able to bring in aerodynamic shape to the contour of the car. Now, when I am doing a computational model of that physical system, if I don't bring in that styling accurately, then my aerodynamic performance will not be captured properly, right? So, you have to have curved elements to be able to model the geometry, but when you look at designers, they would like to have a free hand in shaping, styling. They are not concerned or limited by what you would like to be able to model. I can model with straight edges very easily. No, 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 you cannot design with curved edges. You have to follow. You can't tell like that to a designer, right? You should be able to come up with a computational model which is as close to the real world physical system as possible. But with us, like the way we have a linear element interpolation function, quadratic interpolation function, cubic interpolation function. So you will, even to model the geometry, you will only have some f of x curves with you. Okay. With those segments, you need to model this circle or ellipse or some kind of a shape, whatever it is. So you may have done in computer graphics, for example, if you have done a course, curves like Bezier curves, okay, spline fitting. So we may need to resolve such surfaces that a designer comes up with using these simple elements, even if it curved edges. Okay, is that making sense? So that's the first challenge we see, apart from, of course, dimensionality that I mentioned. Once you agree that it is a two-dimensional problem, this is the first major hurdle we are going to face. And a new error which we said is discretization error. I am not at all talking about the error in modeling the field variable variation, temperature, velocity, displacement. Both I said it was there in one-dimensional problem, it would be there in two-dimensional problem also. In addition, you have brought in this new error. Okay, keep that in mind when we are looking for an approximate solution. But to take a step back with due respect to the classical methods, when you looked for closed form solutions to exact differential equations for this problem, did you not make assumptions about the geometry? You would be able to get closed form solutions only for some types of geometry. Otherwise, you will not be able to get exact closed form solutions. These partial differential equations wouldn't have afforded you a solution if the geometry was complicated in any case. So even there you will have this problem, but here the problem is in the form of being able to model that geometry. So we will introduce curved elements. The moment you think of curved elements, I have some problems. First of all, I have to model the curved edge. Okay. Then the field variable over such curved geometries. Then imagine now I have shown in the left side figure 3 curved edge elements meeting. Okay. When they interface on any edge, In the one-dimensional case, there were elements which were line elements, and two elements were meeting only at one point. So, if the field variable temperature, for example, whether you come from this side or you come from this side, at this point, if it is 102.84 degrees, you are satisfied. It's unique number, whether you come from left or right, and it's therefore continuous. But now imagine what happens when two elements in two dimensions, they come across. There is an infinite number of points along an entire edge. It is not enough if at one point temperature is same coming from this side and coming from this element. For all the infinite number of points on this edge, whether you consider them to be part of this element or of this element, the field variable has to be the same, right? And then of course, I mean this is only the field variable. Okay, you can then ask also about the derivatives. The exact solution, if it exists and you are able to find that, that would ensure that not only the field variable but all the derivatives are continuous across these edges. So, in our finite element solution, I am trying to see if at least first of all the field variable fundamentally would be continuous across. Then, okay, that is guaranteed. Could I think of making sure the first derivative is continuous? Now, when I say first derivative, it will be dou by dou x, dou by dou y. Then second derivative, dou squared by dou x squared, dou squared by dou y squared, dou squared by dou x, dou y. All these things have to be continuous for all the points along this entire edge. And that edge is curved. Okay. So, this is an additional problem that we have. Whatever continuity I am able to achieve, maybe just the field variable, may not be the derivatives, whatever it is I am able to achieve. But I plug it in and I do all your weighted residual or variational functional. I have to do some derivatives, differentiation and then integration, right? That integration will be double integral. How many of you have done double integrals evaluation? Or rather, who has not done? You may not remember right now, but you must have done, right? So, then what did you do? You took a strip and then moved the strip along all over. That is what you did to evaluate a double integral. Now, imagine what happens if you have curved edges. See this strip or this strip, and you have to model it and move it to evaluate this double integral over curved edges. So, even though I know that all I need to do is to evaluate this integral, that is in my head, I know I have to evaluate this integral, but to actually sit down and do it is not going to be easy. In one dimension, we did not ask this question at all, it was straightforward. Yes, it is a little more tedious when you went into higher order interpolation functions, quadratic and cubic compared to linear, but still it was fairly straightforward. So, all these points that I am saying are equally applicable when I go to 3 dimensions also. So, I would not really discuss 3-dimensional elements separately in this course. Whatever we are discussing is every point is applicable to 3-dimensional also. Okay. So, all of these are pain points and we need to propose a solution for these things. Now, let us look at another challenge. It is about deriving the shape functions. How did we derive the shape functions in the case of a one-dimensional element? So, I assumed, for example, linear C0 plus C1x over that element in its own local coordinates. Two nodes 1 and 2 or I and j, whatever, C0 plus C1x. So, when x is 0, that is a local x is 0, it has to be F1. When x is equal to small l, it has to become F2. So, that gave me two conditions and I found out C0 and C1. I substituted it back, rearranged the terms, so I could get something multiplied with F0 and something multiplied with FL or Fi, Fj. This is how I derived it. Now let me see if this method works for a two-dimensional element, right? So I take this simple example of a two-dimensional triangular element. 3 nodes, okay, at the corners, vertices of the triangle. Say, let's say temperature is the field variable. T is now a function of x and y. C0 plus C1x plus C2y. Okay. So the calculations are fairly intuitive, right? So when x1, y1, it should become T1. When x2, y2, it should become T2. x3, y3, that function that I am assuming should become T3. So I have 3 equations in C0, C1, C2. Substitute it, x1, y1, x2, y2, x3, y3 are known. They are the coordinates of that nodal points. So I know them. So there are some known constants. That's fine. So I can find C0, C1, C2 in terms of T1, T2, T3 and rearrange the terms. So how does it look? This is how it will look. So C0, C1, C2 would be given in the form of a 3 by 3 inverse. That 3 by 3 matrix will be only nodal coordinates x1, y1, x2, y2, x3, y3, correct? Inverse. 3 by 3 inverse is not a trivial matter, but it is doable still. I can sit down and find out 3 by 3 inverse, which I am showing you the result. So the determinant of that 3 by 3 comes into the denominator and I will do some manipulation. I can find out the shape functions. Okay. Now all these are intermediate steps I am not showing. If it is a two-dimensional structural problem, there are displacements along x and y, so u and v, but each of them will vary in the same linear manner, C0, C1x, C2y. So I can use the same shape functions irrespective of whether the problem is heat transfer or solid mechanics. It doesn't really matter. That's how we did it even in 1D also. So I can do this. The matrix notation I am introducing so that you become familiar. Writing down Lambda expressions will be a pain. So the way I have written it is the nodal variables u1, v1, u2, v2, u3, v3. So if you have more complex elements and more number of nodes, more number of nodal variables, you can just list them down like that. So I am going to simply write it as a matrix n times the field variable at the nodal points. N is all shape functions. Okay. So this is how it would look like. Of course, because it is linear, its first derivative in terms of dou t by dou x, dou t by dou y, or dou u by dou x, dou u by dou y, giving you strains and stresses would be constants, like in the case of a one-dimensional linear finite element. They would be constants. So this is called a constant stress triangle. This is in fact probably the first element or one of the first finite elements ever to have been formulated. This is very simple, easy element. Okay. Now I try to do the same thing for a quadratic equivalent, quadratic 1D, like the way we have done. I want to find a quadratic two-dimensional element, triangular element. So like you had added one more node in between. So along any line I have to add one more node in between to bring in a quadratic variation. So C0, C1x, C2y, sorry, it should have been C3x squared, C4xy, C5y squared. That's a mistake in the slide, but whatever. So you realize that you have 6 terms in the complete quadratic polynomial. Now I know intuitively, it's very easy to understand. When I substitute x1, y1, it should give me t1, t2, t3, t6. But now imagine I ask you to do this t1 to t6 here, c0 to c5 or c1 to c6. Find out c1 to c6 in terms of t1 to t6. So it would be a 6 by 6 matrix of coordinates inverse, and then rearrange the terms. Then find out T as sigma of Niti, the shape functions multiplying the nodal values of the variable. That's not trivial at all, right? So we will not be able to rely on this method, though it is correct method. There is nothing wrong with this method. We know that it works, but to actually do it is a pain. So this is another problem we notice, that all that we have done in 1D finite element formulation cannot directly be applied to 2 dimensions. This is one more challenge. You may almost wonder, then why are we doing 2-dimensional analysis at all, I mean, if it is so complicated. So we have to find, I am listing out all the problem aspects. Now I will find the solution for this. That's how we progress, right? Of course, just a detour, you may have come across this C0, C1x, C2y, C3x squared, etc. So the coefficients, if you arrange, of 1, x, y, etc., binomial coefficients you might have called. So that comes as a triangle. You would have called it probably, what did you learn it as Pascal triangle, right? So here, because the variation is quadratic with respect to x and y, the first derivatives will be linear, so it is called a linear strain triangle. Okay, fine. But I would just take a detour to focus on this Pascal triangle, whether it is really a Pascal triangle. That's how you may have come across it in school algebra. But if you see, this years are important. Blaise Pascal wrote about it. He was born in 23 and he died in 62 at a very young age of 39. Okay, so he must have worked on this in between this period, and we refer to it as a Pascal triangle in school. But if you look at this, even though he wrote it in 1623 or so, our own mathematician Pingala wrote about it in the 2nd century BC. Around 505 AD, Varahamihira wrote about it. Same formula for binomial coefficients and so on. Then Mahavira wrote about it, gave actually another way of writing out this formula equivalent to this modern formula in 850. Then if you 975, if you see Halayudha's work, he gave a more detailed explanation of that rule, and he brought in what you might have come across the term Meru Prastara. That's a mountain of triangles, right? This triangular shape, arrangement of these numbers in 975. We are talking about this being Pascal triangle 1623 or whatever. Not just our own, the Persian mathematician Al-Karaji talked about it in he was born 953 to 1029, so somewhere around that time. I am sure you must have read about Omar Khayyam. Anybody who has not read about Omar Khayyam? After the class, please. Okay. So Omar Khayyam's poetry. Okay. So it is in Iran. This is actually known as Khayyam triangle. Chinese mathematician Jia Jian, I don't know how to pronounce it, around 1010 to 1070 he was there. He worked on this, he proposed this. And in China, Yang Hui presented it very clearly and all that a little later, about a couple of 100 years later. So it is called by name Yang Hui's triangle, not Pascal's triangle. Even in the West, in Europe, you would see others have published this full triangle about 100 years or so before Pascal. Pascal codified it, brought it into a shape, structure, and then brought it, and thereafter somehow the name Pascal's triangle stuck to this. But you must be aware as students of science, engineering and technology about how it has been known to various scientists from not just India, Iran, Asia, China. Okay, that is just a detour. Italy, it is actually known as Tartaglia's triangle because he wrote about this triangular arrangement of binomial coefficients, combinatorics and so on. So now I have given you this historical perspective. When I was discussing it the other day with one of my classmates, he came up with an interesting question which I thought I would pose it to you, and you can spend some time whenever you are tired of preparing for the mid-semester exams over the next 1 week. Why did so many people all over the world, over the centuries, independently think of this question? I have now already told you that over the centuries, independently from whether it is Italy, whether it is China, Iran, India, whatever, okay, people have come up with this. What this 1 x y or 1 1 1 1 2 1 like that, right? That you know the combinatorics formula, binomial coefficients, and you would also have thought of another name for this in this context was, what did you get out of this triangle? What is the other series you got out of this triangle? Sum of these numbers? Huh? What is the other series? If you add up these numbers, huh? I don't hear. I am growing hard on hearing. Unless you, when you have a doubt, you will stand up and ask me and all that. When I ask a question, your answer will be very muted. What was that series called? Huh? Pardon? Fibonacci series? Have you heard of that? So this led to all those things. Now the question that when we were discussing over the weekend, that why did so many centuries, so many scientists around the world think of this problem? I mean, what was the motivation? What were they trying to solve? Okay. So those of you who are interested can explore this angle. It would be interesting to see, why did Pingala think of this, for example? What was he trying to solve when he came up with this? Why did a poet like Omar Khayyam think of this? Okay. So
because these actually represents in nature, we see some kind of like structure, like the shapes will be like this. Like if we are talking about Fibonacci, there is another like golden spiral. Every nature, like even whatever the snowflake will be formed in a specific pattern. So like even the snails,
so you would be nice. Yeah, I agree. So it would be interesting for you to explore this. They were interested in games, not just you now on video games. They were also interested in games at that time. They were trying to probably solve some problems of agriculture. They were trying to compose poems and they wanted to understand the structure, grammar. So you can explore this angle. I don't want to detour too much, but you can explore that. Now another interesting problem that comes is that if I am looking at not a triangular element but a general quadrilateral element, suppose I have now 4 nodes. So C0, C1, C2, C3. C0, C1, C2 is clear. See, constant x and y. Now with respect to C3, what do I attach? Should I attach x squared or xy or y squared? This is a new problem that I have. Right? I didn't have this problem when I talked about quadratic element in 1D. I just added one more node, C0, C1x, C2x squared, katam. Okay. But now with a 4 node element, I don't know what should be that 4th fellow. If I put x squared, why is it important? If I put x squared, then it is an f of xy, right? Field variable, temperature or velocity or displacement, whatever. I am giving a tilt more sharper variation towards x compared to y. And now what is this x or y? I don't know. It depends upon how the element is oriented when I am modeling a two-dimensional domain. Okay. So it is not something universal. It is along elements local x. In terms of the physical problem that I am trying to solve, I don't know what that local x that I have put when I am formulating the element in terms of x squared. I gave a preferential variation with respect to one coordinate vis-a-vis the other coordinate. How it translates into actual application, I don't know that. Similar is the case with y square. So if you want to be able to build a powerful software which anyone will use for any problem that he or she is trying to solve, and they themselves are not formulators of this element, they are just using your software, then you should not be biasing the solution in any which way. If you think of that type of logic, then I would go for xy. So then it is a bilinear. On an x constant line, it is linear with respect to y. On a y constant line, it is linear with respect to x. So I will go with xy. But if I know that it is an element that I am formulating for my particular research problem, where I know that the variation with x is sharper, so I would probably put x squared. You understand my point? So you have to keep this perspective in mind when we are formulating these elements. So I will just kind of summarize all the points that we have discussed, and then now what is the solution? Our point is about to find a way out of this set of challenges, right? So the solution that I propose is, let's not do it in terms of x, y coordinates. I would propose to use what are known as natural coordinates. It's a new coordinate system, zeta eta frame, where what is so special about this, or why are they interesting to me? So you see the left hand side and the right hand side pictures. The left hand side picture shows this mathematical or computational model coordinates, which are zeta and eta. In those coordinates, the element will always be a perfect square of size 2 by 2. Edges will be straight. Coordinates vary from -1 to +1, -1 to +1. Okay. All my integrations, differentiations, everything that I would do will be in this coordinate frame. Can you see it? No. All these things are hidden inside my computations. The real physical world element is what is on the right hand side, which is in terms of xy coordinates. The field variable, temperature or displacement, etc., is in the right hand side picture. The derivatives we are interested in of the field variable to compute heat flux along x direction or y direction, strain and stress along x and along y, these are all in terms of real physical coordinates x and y. So what I am going to do is to keep doing this back and forth. So xy to be related to zeta eta. So the derivative that I need, I will use chain rule of differentiation and bring it in terms of zeta and eta. The shape of this could be a general quadrilateral in the xy plane. But in my formulation, using the mathematical structure I just now coined, it would be a square. So that quadrilateral is mapped, every single point in that quadrilateral is mapped into this square. Now, it's easy to visualize. If this mapping is linear, then a straight edge here will become another straight edge in the real physical world. But if this mapping xy to zeta eta mapping is non-linear, this will remain straight edge, but in the xy plane, this can become a curve. Is that clear? So I am going to meddle with this xy to zeta eta mapping function, so that in the xy coordinates, whatever it may be, in the zeta eta coordinates it will be a straight line, in the xy it may be some curve. So I don't need to worry about double integrations on this kind of a curved edge, but I will do over this square domain. So I would want you to think in terms of these natural coordinates, and when we meet again after the mid semester, I would be discussing from this point of view of formulating the natural coordinates for quadrilateral elements, that is rectangular domains or triangular domains, and then do all these computations back and forth, etc. xy is where the physical action is, but all the mathematical action happens in zeta eta. Okay, is that okay? So on this framework we will stop here for today and then continue in the next class after the mid semester. All the best for your mid semester exam.